rejuvenation of oil production through well intervention from mature sand of multi-layered brownfield Nawagam Camby Basin. Good morning, sir.
Very good morning to all of you. Myself, Sourav Mahato, Manager Reservoir from ONGC Ahmedabad Assets. Actually, I am going to present the rejuvenation of oil production through oil intervention from mature sand of multi-layered brownfield of Camby Basin. Actually, this is the case study of the of a field of Camby Basins. Now I have taken this data from IEA. You can see that nowadays, the conventional oil field, discovery of conventional oil field is decreasing day by day, whereas the demand of oil is increasing year and year. So the additional recovery over this easy oil, it totally depends upon the induction of new technology and effective reservoir management strategies. Now this is the outline of my presentation: introduction, production performance of the field, challenges that we are faces by us, applications, and its results, and now next is conclusion. This is the index maps of our field. Basically, it is situated in the southern part of Ahmedabad-Tarapur tectonic block of Camby Basins. Now this is the general stratigraphy. I am not going too much details because it will limited to 15 minutes. So this is the general stratigraphy. Basically, 4 producing sets are there. That is K3 plus 4, and which is the member of oval formations, and upper pay K9 and 10 developed throughout the field, and it belongs to Setha member of middle Eocene, and middle pay, which is developed to the limited extents in western and central part, and lower pay, which is subdivided into 4 sublayers: N21, N22, N3, and N4. Basically, I will majorly focus about the lower pay. This is the general geology of the of this field in this Camby Basins. Mostly siltstone, silticier, shelly, and coal layer is there. But siltstone is the main reservoir rock, and 41% of total OIP lies in lower pay, and 49% of total OIP lies in the upper pay. And the small pool, that is middle pay and K3 plus pay sands. Now this is I will main focus on lower pay because this is the case study of this rejuvenation is for lower pay. So this is the structural variations map of top of lower pay. The blue lines are the injector. You can see that structure is seen as an asymmetric trending west-northwest to east-southeast with a gentle dip towards northwest and southwest direction, and steeper dip towards northeast and southeast direction. Lower pay deposited in the alluvial fan depositional environment results in structural high in central part and gently dipping towards the western part of the fault. Now coming to the field development history and production performance. The field was discovered in 1963 and put on production in 1967. The field achieved the highest production in 1977 of 1050 meter cube per day. After rejuvenation of this lower pay, we have you can see that we have another gate and peak of production after a gap of 27 years. You can see the pay-wise production distribution of these fields. There are 4 pay. The production distribution of 4 pay zone is shown here. You can see that in the left-hand side is the liquid production, the right-hand side is the oil production. You can see that how within a span of 2 years, how the liquid production has been doubled, and you can see that oil production has also been doubled in these fields. Now this is the production performance of the lower pay. You can see that it was producing from 1967 and exhibits all type of behavior like maturity, reaching the peak production, and and could not attain the same even after various efforts. Now, after adopting different methodology, we have got another peak, which is 347 meter cube per day after a gap of 41 years. These are the challenges that are faced by us. The main challenges of the lower pay is the log correlations. Due to an interpretation, due to flat gamma ray, it was very difficult to distinguish the sublayer of this lower pay. The wide mineralogical variation throughout the field. So mineralogical variation very heterogeneous. So stimulation, the designing of stimulation is also depends on that. Identification of bypass well, zone transfer where there is opportunity, or zone addition where there is opportunity. Subhydrostatic pressure, water breakthrough in the nearby producer where there is an injection, and the identification of suitable stimulation job. Now, how to overcome these challenges? What we have done that first we have gone through the whole log correlation of the total field. Then after understanding the total whole field, we have reinterpreted our log, then identified the bypass well, and we have done the zone transfer, zone addition where there is opportunity. Then we have seen the mineralogical variation. Based on the mineralogical variations, we have done the stimulation designing, and the long pending revival well, which were non-flowing due to high water cut or poor influx. So we have revived that one. And final is the decision, because decision is the main key factor, key element to enhance the production. Because if the decision is wrong, then the whole go into the fan. Whole success will go into the fan. So decision here in the lower pay, the decision was the main key factor to enhance the production. This was the log correlations where we have seen there is a mismatch of correlations in the profiles. You can see which was highlighted in the red. How these correlations was different from the earlier one. So we have corrected this one as per our understanding and reinterpreted our log. Now you can see that here in the pink color, it is marked that some zone in the upper pay, the high gamma peak was considered as the marker. So in the earlier convention, it was not perforated. But what we just tested in one well, and it gives the success. Now you can see how these oils AB2 to 7 has 4 times liquid productions from the base productions. Basically, this is due to the zone addition. After zone addition, we have designed the nitrified acid jobs, and after nitrified acid jobs, we have gone to around 50 meter cube per day of liquid productions. Now the identification of bypass well, based on the oil behavior, oil performance analysis, nearby oil performance analysis, and our understandings, we have seen that in some of the wells there is a still opportunity to go back in the lower pay. So just like an example, in AV2 to 9, one well which was completed in the middle pay, you can see because this was zone transfer due to 100% water cut, and the liquid production was 10 meter cube, but produced only water. So we have breeze plug it and zone transfer to the upper zone. Now, after analyzing all the data, we have thought that yes, there is still an opportunity to produce from this lower pay. So again, we have milled the zone transfer, and we have cement squeezed all the intervals and just selected perforation intervals and done the nitrified acid. And you see the beauty of the productions. It has increased up to initially 60 meter cube per day, and now producing around liquid production of 30 to 40 meter cube per day. And nitrified acid job is favorable for lower pay. However, the response of the nitrified acid job was not successful in each well. So what we have done, that high-tech mineralogical log was recorded in these 2 wells, and we have taken the interpretation of this high-tech mineralogical log and incorporated with our core data. And after integration of this core data, we have seen that in the western part there is the nitrified acid job is not successful, and in the eastern part the nitrified acid job is successful due to the calcareous materials. And in the eastern part, large number of microvugs are also there, so which is absent in the western part. So based on this mineralogical variation, we have designed two types of stimulation. One is the nitrified acid job and followed anionic surfactant followed by nitrified acid job and the hydrofracturing jobs. Now you can see this is the eastern in the left hand side. In the left hand side AB273, we have done nothing. Just we have done the anionic surfactant and nitrified acid job, and you see the jump of production of 4-fold from the initial current production. And in the right hand side, it was basically situated in the western part. So we have tried several things in this AB275 wells. Nitrified acid job, several types of nitrified acid job, additional perforation, nothing has been, production was not improved. Lastly, it was just fall as an ideal. So what, based on our analyzing data, so what we have done that, let's do it at a hydrofracturing, and you see there is a beauty of the production. After hydrofracturing, this oil got around 30 meter liquid production of 30 meter cube per day initially on cell. Later on, it was decreased, and now it is producing an artificial lift and sustained production of liquid production of 12 meter cube per day. Now revival of non-flowing wells. The non-flowing wells which were pending, which were non-flowing due to poor influx or some high water cut, like an AB121. So what we have done, we have gone there and we have interpreted all the data, and we have done the selective perforation and see the beauty of the productions. Next is the reservoir management. Actually, reservoir management is the main key factor to improve the production. So here is the peripheral water injection is there. Some oil producer was also in the, just like AB92 and AB51, the water injection has been started in the structural down dip, from structural down dip to up dip directions, and improvement of injectivity data. Now the water flood surveillance, basically, after revised log correlation, the water injection plan was chalked out, and for execution of that, like pressure survey, for injection water movement, injection logging study for identify the sublayer accepting water. And based on that, we have done first time profile modification job in lower bay of a reservoir temperature of 130 degrees centigrade. And you see the beauty of the production. In the nearby producer, the water cut has reduced drastically, while the oil production has improved significantly. So now you can see, I have taken the data from the wells which are in the April 2016. You see, the field was producing around 300 TPD, and we have gone it's up to 500 TPD. This is just because of rejuvenation of this lower pay. You can see in the right hand side that it was producing around 120 TPD in 2019, and we have gone up to 300 TPD at present day. Now this is the conclusions. Conclusion is that in the central and eastern part is right candidate for anionic surfactant followed by nitrified acid job, while the western part is right candidate for hydrofracturing jobs. These are the acknowledgement that I am very highly indebted to ONGC and ONGC management. Also the executives of Ahmedabad Assets, ONGC Digital Library, and this is the view of the author. It's not reflect the views of ONGC. Thank you.
Thank you, Sourav. We appreciate you. Any questions from the audience for Mr. Sourav? All right, thank you. We'll move to our next presentation. It's going to be about hydrocarbon exploration opportunities in a Deccan basalt play, Western Indian basins. The presenter is Mr. Chandra Mohan.
Good morning, everyone. So I'll be talking on hydrocarbon exploration opportunities in the Deccan basalt play. It's a bit unconventional, so we generally find hydrocarbon in the sedimentary basins. But here I'll be talking on how we can get some hydrocarbon from the basalt plays. So it will be the outline of the presentation is a bit it's a bit squeezed in the 15 minutes. So I'll talk on what is the hydrocarbon play introduction, and what we mean by the hydrocarbon that basalt play, and what the data we have to get that knowledge. And I'll show some of the interpretation based on the wildline logs and the well observations. And finally, some results. And there are no results actually. It's a summary and the conclusion. Still, we can discuss more on how we can move ahead in the hydrocarbon play. As you can see from this map, so the green area you see, the western part of India is covered by the Deccan basalt. So that is there are some surface exposure. There, as you can see, the dotted line, that is the western, we can see some extension towards the offshore region. So roughly it is covered all our western basins, so which are main producers for India. So like Bombay offshore and what we say Badmer, southern part of Badmer to entire Cambay and Saurashtra as well as Kutch. So my study is based on the Kutch region. So we had recently drilled a well. So 1.5 kilometers of basalt we drilled. So we have some unique observation on that. So that's how we will go and what we think on that play. So before I go further, so just basic definition, whenever we say the Deccan, basalt, so we always imagine this kind of rocks. So there are categorization from the basic to mafic rocks. So you can say from ultramafic to felsic rock. So it depends on how the silica content varies. So our main rock of interest are actually on the intermediate, whether mafic or intermediate layers. So where we see most of the Deccan basalt is majorly constituted by the intermediate and the basaltic rocks. On how that Deccan basalt is actually in place. So you can see the bottom corner. So there are two kinds of volcanism. One is called intrusive, other is called effusive. So intrusive volcanism, we get in such kind of basins, we get both the features, both effusive and the intrusives. So intrusives are which are already buried, and extrusives are what we get on the surface. So the big block diagram, you can see all the pink layers. These are the different types of flows, and which are actually mostly flowed when India was at the Reunion hotspot. So it's a roughly late Cretaceous volcanism, but it has multiple layers, multiple flow layers. And within all flow layers, we have some age gaps. So these age gaps sometimes are filled by the sedimentary layers, which we call intratrapians. But sometimes these are not having any sedimentary, so these are weathered. So I'll be talking on the only weathered part, not on the intratrapians, what sedimentary layers. So what we see in the weathered part. So this is just a difference, one layer, one outcrop. So what we see on that multiple flow, if you zoom in and into that one of the flow layer, so what we get a hard volcanism. At the top, we get some, we can say weathering. So that is called the weathered layer. So generally, what we believe, if there is an age gap, it has some weathered topping. So how that weathered topping has some potential, that's how I would be talking on that. So this is just a snippet of whatever data we have. So we have seismic data. So that is a determined when we do the interpretation part. We drill the well, so we have a basic well logs, and during during drilling we have some gas data as well. We have cuttings data, and finally we did some wildline logging and the basic wildline logging, the cross plot. So I'll be showing most of the interpretation based on the wildline different cross plots. And how we based on that wildline outputs, how we imagine what kind of actually setting was there. So that's how we use our outcrop images as well as the not depositional entrapment models actually. So this is all summary of, I'll not go into detail. So all the summary. So in the volcanic rocks, there are different types of different reasons how the porosity can be developed. So broadly, it is categorized in the primary porosities and the secondary porosities. So primary porosities are something like vesicles or during that emplacement. And the secondaries are mostly due to some mineralization, fractures and other things. So I'll be talking mostly on the primary part. It's not a primary and secondary. It's both in the transition. So because I'll be talking on the weathered part only. So that depends on, it is not exactly the volcanic porosities, but it's derived from the volcanic rocks. So in this section, I am showing multiple cross plots. You can say left-hand side, the density and sonic cross plots. And all the colors are based on the porosities. You can see the color bar going from 0 to 40%. So the shaded part on every cross plots is showing the hard volcanics, and which is roughly cutoff of around I think the porosity cutoff of 15%. So you can say all the colorful dots, these are higher porosities. So roughly more, so not 15%, more than 10% in fact. So more than 10% is falling on this colorful part. The blues are we can say the hard volcanics. So these are the key findings what we observed during the drilling of that. And if you see the density depth diagram in the right hand corner, so you can see there are variations. It's a 1.5 kilometers of Deccan basalt layer. There are variations from the high porosities to low porosities. So that's how we see there are some interesting zones. The porosities are extremely high, sometimes more than 40%, and the depth of the basalt is above this basalt layer. We have 1.5 kilometers of tertiary sediment as well. Other interesting trend which we generally consider in the volcanic rocks, there will be compaction trend, right? Compaction trends are generally in the sedimentary basins, sedimentary rocks. But what we see here, you can see the depth versus density plot, and there is a gamma overlay as well. So there is a gamma also a differentiator for that. So all the shaded part in the left hand corner is actually these weathered layers. And broadly, we can categorize mafic and ultramafic, which is density is more than 2.8 and above. And below that, we have all weathered zones. And you can see the variations. And you can see, in fact, this is very interesting trend. There is a compaction trend within volcanics. So that is a bit of, in fact, when we observed this, so we were surprised how we can get the compaction trend within the volcanics. But this is how we see the thought came. So there may be some potential. And when we checked in the seismic, so we see the variation as well. So seismic image is wiggles are plotted here, and the top layer have lots of seismic reflections. You can see the top red layer there, red arrows are showing a distinct seismic character as well. And the bottom is a massive one, so this is a mid-intermediate layer. So where is density is bit clustered, and it is going towards the felsic part. So that's how the initial flows were mostly due to the partial melting, and later flows are mostly in the mafic zones. And there are some other cross plots. This is sonic resistivity, and resistivity, one more thing, resistivity also a good differentiator for the volcanic rocks. So high resistivity goes as high as 200 ohm meter in the hard volcanics, but in the weathered zone, the resistivity range is quite low. And within that low layer, this is a big trouble for the petrophysicists as well. So how they calculate the saturation in the volcanic rocks. Still, there are actually people thinking how to calculate the saturation within the weathered zone. So because the background, there is no background, we can say, measure or background reference for that if we say that there is a saturation, hydrocarbon saturation or not. And these are some of the cuttings, how the weathered zones are differentiated. The red ones, you can see the weathered zones. Even the cuttings also differentiates, and the black ones are the mafics during drilling. So just to summarize all, so what we got, there are other studies as well integrated while we are drilling that. So we got some gas elevation as well on that weathered zone. So overall, if we plot all the porosities, so as I shown the image earlier, so there is a hard volcanics and the topping of weathered one. So there are multiple flows, and the porosities goes as high as 35% in some of the layer. And interestingly, it has actually compaction trend as well. And overall, if you plot all these, so roughly 18% kind of porosities, average total porosity we can get here. But most of the layers, especially in the top, are going as high as 25% porosities. So these are the interesting zones, and that's how our play model comes in the picture. So how can be in fact, Cairn Oil and Gas is already producing from this play in the Rageshwari. This is called one of the field we have in the Bardmer called Rageshwari gas field. So we already producing from this kind of play. So it's a good gas rates we're getting. And the play model is very simple. If there is a Paleocene source rock, so mostly in the Western Indian basin, so even is Bombay offshore or a Cambay or Bardmer or even Kutch. So Paleocene has a very good source potential. So it's mostly Paleocene, Eocene is the source. If that is mature, so it can easily migrate at the basement high. If there is a node Mesozoic. If there is a Mesozoic in case of Kutch region, so Kutch region we have a proven Mesozoic basin subbasalt, and there are very good potential in the Jurassic source rock. These are transgressive shales. These shales are well mature for the gas, and this can migrate towards all the traps which are actually in the weathered zone of the basalt layer. The only question is how we test it or how we produce it. In fact, the testing, there is no scheme for the testing for this. There are some attempts like we do in the Bardmer basin in the Rageshwari field, we do in the open hole testing, and the only indicator for the gas zone or interesting zones are high gas elevation during the drilling. Otherwise, we attempt some NMR logging as well, advanced logging, to quantify some of the saturation, but that is also not a fixed rule. But the only indicator, there is a background elevation from the background is the only indicator. So there is actually it's a thought for everyone. So I think people should, if they're going to some Cambay or some of the basins, so they should deepen the well and try to test probably for the open hole testing. So that would be the best way for the testing these top play. So at least 400-500 meter into the basalt, we see a good potential. So going forward as a Cairn, so wherever we will be going, so we'll be testing this play. So just to summarize everything, so it established weathered layer versus, and there is a clear distinct trend in the compaction as well. And there are very high porous zones within the basalt, which is, I think, not reported very frequently. There are intertrapians, many papers have been discussed on the intertrapians. There are sedimentary layer in the trapians, but not on the weathered toppings. So the weather topping is something interesting, and I think it covers the vast range of the basin. You can see all the green layers. In fact, wherever there is a Deccan basalt layer, so the potential is still, that the hydrocarbon potential still hold in these all basins. So key here is we need to establish some of the testing measures as a whole, oil and gas community or the GNG community and the petrophysics community. We should be thinking on the how we actually calculate the saturation within the basalt and propose the testing plan for this. Either it's an open hole testing or maybe frac or some other testing. So the only ask here is actually the oil and gas operator. Let us go with if you're drilling some wells, let us test this play as well and deepen well. Probably that will not cost much. Most of the reservoir like Bardmer or the Cambay, we're going up to Eocene, so there is some Paleocene sales and below. At least in the not in the deeper in the deeper depot centers, but on the fringes part, these are the ideal locations. And the northern Cambay, in fact, Cairn also has a very good. We would be drilling this play in very soon. So that's how I think we should be getting some good potential on that as well. So that's all from my side. Thank you very much. So if any questions I can take.
Well done. Thank you, Chandra. Do we have any questions from the audience? All right. Thank you, sir.
Thank you.
Next up, we'll have Nikunj Patel with Oceaneering. He'll be presenting an ROV-based multi-string hot tap, safer and cheaper unconventional access to subsea wellheads for intervention.
Good morning, everyone. Nikunj Patel, I'm a VP of Engineering and Technology with Oceaneering. Today's presentation, I'm planning to provide an overview on one of the projects we did in Southeast Asia last year. That's very unique example of how Oceaneering can solve customers' unsolvable problem. So one of the operator contacted us. The project was about decommissioning. They were planning to decommission around 120 wells offshore. During the inspection, they find out that there may be a gas trap in low pressure annulus onto the wellheads. Now that's a big HSC risk. They cannot decommission the wellhead when there is a gas into the low pressure annulus. And the scope for decommissioning for them is to remove the wellheads below the mud line. So when they contacted Oceaneering, we come up with a very unique solution. we come up with the idea that how using the ROV, not the diver, how using the ROV, we can drill the hole onto the annulus, release that pressure in a controlled condition, eventually go back, cement the annulus and provide that annulus the integrity so it can be decommissioned. Now, this is never been done worldwide. We have around 20 weeks to execute the project, all the way from engineering to designing, building all the system, qualifying it, going offshore and performing the operation. So again, the overall idea is how to design the system which can be deployed from the world-class vessel. No rig. This is not the rig-based operation. We can go from any world-class vessel. We can take the world-class ROV, go with the unique design, custom design, suite of tools, and perform the operation. So let me So as soon as we start the project, the first challenge we have to face is what is the right size of the hole we have to drill on the wellhead without compromising the wellhead integrity, but same time the hole needs to be big enough so we can do the cement job. We deploy the global team to work on that project. We have a team from Australia who took the lead, but same time we have a team from India, UK, US. They all collaborated based on our experience to solve this problem. Let me walk through the sequence of operations. So now think about subsea wellhead. So the only thing subsea is a wellhead sticking out. Step one for us was to deploy the clamp mechanism. And that clamp was deployed on a downline. It's a ROV operated clamp. We clamp around the wellhead very strongly. The main reason for the clamp is we have to drill multiple holes. We have to drill a hole on 36-inch casing. We have to drill a hole on 24-inch casing. And all that holes needs to be exactly on the same axis. The precision of the holes needs to be in thousands, and let me say millimeters if I use the right unit for the right region. So we're talking about very sophisticated CNC operation subsea. So as soon as we install the clamp, the next step for us was to install the PAR tool, pressure annulus release tool. This is custom designed CNC machine. This tool has a RPM sensor, force sensor, thrust sensor. This is operated by ROV from surface. So this tool clamps on the clamp, and then we drill a 3-inch hole on a 36-inch casing. As soon as we drill a 3-inch hole on a 36-inch casing, we retrieve the tool and change out the drill bit. And then on the 24-inch casing, the next casing, we created a very flat surface. So we did not penetrate the hole because there is a gas on the other side of the wall. Now pipe has a curvature, so we cannot seal on the pipe. So that's the reason we have to create the spot face. Once we successfully created the flat, then we retrieve the drilling tool and install something called seal assembly. Next. So seal assembly locks onto the clamp, it extends to that flat face and creates the face-to-face seal. What that means is if we punch a hole, if there's a gas, that gas doesn't go in the atmosphere. We can contain it. We can connect with the hose, retrieve it on a surface and flare it. Once we installed the seal assembly, we did the pressure test and everything worked out really good. Then we deployed something called ROV hot tapping tool. This was the first subsea hot tapping tool design which was operated by ROV. So we deployed the hot tapping tool. Using the hot tap tool, we were able to successfully punch a hole onto the low pressure annulus. And here we find gas. There was a gas. As soon as we find the gas, we close all the valves And then we connect with the downline hose. And we were able to retrieve that gas and vent that gas out. In short, release the gas in a controlled condition. Once we find out there is no gas remain in the annulus, next stage for us was to cement it. So we use all the surface-based equipment and cement the annulus. The objective for cementing is to make sure that we can seal that annulus for a good. The gas cannot trap back into the annulus. Once we cement the annulus, we came again and did the pressure test to make sure that cement is sealing. So as you can see, this was a lengthy operation. Very systematic step-by-step operation which requires multiple tools, multiple testing. So this was a very complex project. From the day one, we have to design so many different type of custom tools, which was never designed before. But one of the lessons learned for this type of project is whenever you do this type of project, especially when ROV or robots are going to operate those tools subsea, you will face so many unknown conditions. So you have to do the SITs. SIT we call Site Acceptance Test. So before you go offshore, we drill hundreds of holes in the SOP environment. We repeated the process hundreds of times to really understand how the system is going to predict, how the tools are going to behave with the different material when we go subsea, what type of things we will encounter which we are not thinking through. Especially you work with projects like this, always you have to have your plan B, plan C, plan D. Because you never know. You have assumed a lot of things. You never know what's going to happen. One of the biggest risks in front of us was what happens if we punch a hole, release all the gas, but we cannot cement the annulus. If we cement, it's still leaking. What to do? In that case, we have to design a custom metal-to-metal plugs. So these were the plugs designed to operate by ROV. So in a worst case, we can release the pressure and ROV can install these plugs. In that case, even if the pressure is going to build up, we can contain it. So overall, very successful project, huge project, complex project. Oceaneering, we do end-to-end engineering, project management, and execution. What that means is we do the full engineering, we do full project management. We have to use for this project a world-class vehicle. It was a 2 ROV operation. One ROV is doing all the work, the other ROV is more observation ROV. The layout you are seeing is the back deck operation. You can see some of the big equipments for cement operation. And here were some of the results. So we were able to successfully remediate 41 wells. Think about doing this operation from rig or jackups. We did from vessel, which was a fraction of cost for the customer. So we were able to save customer their 80 to 90% of the cost. So again, very successful operation. We did 2 campaigns, remediate 41 wells, and client is already onto their actual project of decommissioning this well as per their original schedule. So this project was specifically for decommissioning. But what can be the other application of this type of technology? So we find out, working worldwide, when we're talking about Gulf of Mexico, Chevron Tahiti, when we're talking about Nigeria Agbami field, there are fields where we find out that there are live wells where operators are producing, but same time they find out that lower pressure annuluses are building up the higher pressure gas. There are cases in Canada where because of that problem, the wellhead has been collapsed because the low pressure annulus are not designed to trap pressure. So Oceaneering were able to successfully use the same technology And we call pressure annulus release operation on those wells, where we do the exactly same operation we did for decommissioning. We drill the wells, the actual 36-inch casing, 24-inch casing, 16-inch casing, we release the pressure, and then we install the sensor system inside those pools. And we connect those sensors to the tree or manifold auxiliary communication system. So you can monitor this pressure from surface. So again, the project I was explaining was purely decommissioning project, but the same technology can be used for active pressure monitoring for some of the wellhead. So hopefully this project give you really good overview of type of problem oceaneering can solve. This is just a one-off example, means we do very diversified different work. So keep us in the mind whenever you come into the bind for your offshore operation. We can be a big help solving your problem. Thank you.
All right, thank you, Nikunj. Any questions or comments from the audience regarding Mr. Patel's presentation? All right,
Thanks.
that'll bring our next speaker, Mr. Analava Chakraborty from Indian Oil Corporation. He'll be presenting petroleum systems modeling as an exploration tool, a case study from Rub al Khali Basin, onshore Abu Dhabi.
Thank you. Good morning, everyone. Honorable Chairperson, fellow delegates, and speakers. So the title of my presentation is quite a mouthful. Petroleum System Modeling as an Exploration Tool, a case study from the Rub al Khali Basin, onshore Abu Dhabi. So this will be the presentation flow. I'll be talking a bit about the study area, the workflow that we adopted, the outputs in terms of the 1D and 2D petroleum system modeling, and the conclusions followed by the well results. So the block is located in northwestern UAE in Abu Dhabi in the Rub al Khali Basin. It's about over 6,000 square kilometers in area. It's in an exploration appraisal phase, and there are two pre-existing areas with oil shows in the block. So we started off by building the depositional model, and we reconstructed the burial history. We made the lithostratigraphic framework within which we started the work. We defined the reaction kinetics of the source. We made the thermal model, and finally we were left with the outputs in terms of the hydrocarbon generation, maturity, and the expulsion. And finally, when we went to the 2D part of the exercise, we also modeled how the hydrocarbons flowed along the section, along the 2D section. So from a regional level, we went to the block level. And on the left, you can see the structuration in the block is such that there are two lows, which are in the northwest and the southeast, which might be possible kitchen areas. So these were the main areas of our investigation. And the yellow part is a north-northeast, south-southwest trending anticlinal area, which is the more or less the target area for our wells. So we started off by building the stratigraphic framework, and this served as the main block framework within which we started to work. And so we started by defining the age limits of each of the formations, the individual formations. We defined the petroleum system elements. We defined the lithologies and the facies. So the lithology accounts for the depth versus porosity, and the porosity versus effective stress, along with matrix properties such as thermal conductivity. And we also incorporated the major regional erosion hiatus events like the unconformities which we could find throughout the stratigraphic record. And from the 1D, we defined individual 34 layers, and we scaled it up to 21 layers when we went to the 2D. These are the main three source units which we delineated for the study. So the primary source is the Dia Formation, which is the regional Jurassic source. This is followed by the Bob member of the Shuaibah in the lower Cretaceous, the green star there, and the Shelai Formation in the middle Cretaceous. So the output that we were left with was the structural framework at the block level. So I'll delve a bit into the geology of the area because it's important to understand the source rock characteristics. So during this time, Permian to Cretaceous, the Arabian Plate was a vast extensive shelf at the margin, northeastern margin of the Arabian Plate. And it was quite stable, but there was some differential intraplate subsidence, which led to the formation of local intrashelf basins. which were conducive for the source rocks to deposit in, and they had anoxic conditions, restricted circulation. This was in a mid to outer ramp setting, and so it was below the storm wave base, and so the kerogen was preserved in this kind of a setting. So the first one is the Ab formation. It is a regional source in a similar intershell basin, like I said. This was followed by the Bab member, which is associated with rudist reefs and algal buildups, which act as a reservoir of the Shueba. So it's associated, the Bab is actually a member of the Shueba, deposited together concurrently. And followed by the Shelife, which was deposited in obviously a similar intershell basin, but during this time the intershell basin was more extensive and expansive than during the Bab deposition time. And Shelife is associated with the higher energy Mishrif phases at the basin margins. So these are grainstone to packstone and rudist algal mounds. So with that understanding, we went back to the literature and the data, and we tried to find out what kind of source rocks we were dealing with. We found that we were dealing with primarily a mix of type 2 and type 3. We defined the kinetics as such in the software using Pepper and Corvy's kinetic classification. We also incorporated the initial TOC and hydrogen index values because they are representative of the original source rock, because otherwise they would not truly reflect the original nature at the time of deposition. And finally, we were able to model the transformation of kerogen to bulk petroleum after we defined the kinetics. Then we needed to define the boundary conditions of the model in terms of a working heat flow model. So there are two boundary conditions, the top and the bottom one. So the top boundary condition was the paleo sediment water interface temperature, which is the temperature at the interface of the name implies, the interface of the sediment and the water column. This is a function of the paleo water depth and the latitude. The Arabian plate was more or less near the equator during this time, so it didn't move much. So this was the top boundary condition. And the bottom boundary condition is a result of Earth's natural heat flow due to its naturally occurring radioactive isotopes, the accretionary heat, and also heat from the dense core sinking, the frictional heat. This accounts for this is correlated with the major tectonic events, which in this case was the opening and the closing of the Neotethys, as you can see at the bottom right, the two spikes right there. So this was the bottom heat flow condition in milliwatts per meter squared. So once we ran the thermal model, it was important to calibrate it and ascertain its accuracy. So we did that by taking the regional heat flow profile. As you can see, the curve on the left, the brown curve, number 1 is the basinal temperature profile. And the curve number 3 is actually a temperature log we had from a nearby well, which is about 500 meters away, which is a localized temperature profile. And curve number 2 is the model, the result of the model that we ran. And you can see that it's well constrained within the local and regional profiles, especially the zones of interest. So this was done at a known well, well A. We also created some pseudo wells at various locations, randomized throughout the area to further calibrate the model at these different locations. So with these top and bottom boundary conditions, we were able to check the accuracy of the thermal modeling at these various locations of the pseudo wells, and we were left with a well-calibrated thermal model. So with all of these inputs, the next step was the outputs, the 1D outputs. The 1D outputs were generated at the well levels, in situ outputs. And we saw that the regional Diab formation that's highlighted in red there is actually generating oil at present and falls within the oil window, peak to late oil. It started generating in the Santonian in the mid-upper Cretaceous, and it started expelling. So expulsion is when the transformation ratio of the kerogen exceeds 50%. So it started expelling closer to the Maastrichtian in the late upper Cretaceous. The Bab member is in the early oil window. As I said, the Bab was a localized source, so it is generating in some places, not regional like the Diab. And the Shelife was found to be immature at this location. So well B is located on the anticlinal trend, you might recall from the first slide. So this was the understanding from the 1D. Now with the understanding from the 1D, we actually went to the 2D. We wanted to find out how the Diab was behaving across a pan-block scale. And for that, we took a section, a northwest-southeast oriented section, which was about 90 kilometers in length. We wanted to find out how the fluid movements and how the expulsion was occurring along this section. So on the top left, we had the Jebel Dhana low to the northwest of the block. And then we had the anticlinal area, the north-northeast, south-southwest trending anticline. And to the southeast, we had the Gurab low. It's the central part of the low is further down to the southeast of the block, but we have a rising flank of the low, which falls within the block. And we chose this section based on the existing well locations, the pseudo wells, as well as the structuration within the block. The additional input that went into the 2D was the layer cake model to capture the heterogeneities along the section. So we modeled the facies, we modeled the lithologies, and we defined them for individual layers along this entire section. And we already had a well-calibrated thermal model. So by combining all of these along with the reaction kinetics, we saw how the two lows were behaving. So this is quite a busy slide, I'll take you through it. So if you look to the map on the left, the two lows we are interested in are marked by the green star to the top left at the northwest and the yellow star to the southeast. So we wanted to find out which of these two lows were more likely to contribute to the generation and expulsion, at least within the block area. And coming to the bottom right, where the table is there comparing the two lows, we can see that the Jebel Dhana low to the northwest actually started generating and expelling much earlier than the Gurab low. So the Jebel Dhana low started, at present, it falls in the late gas, in the wet gas window. And it's almost been entirely transformed to hydrocarbons, so 97% transformed. It also started expelling, generating and expelling much earlier than the Gurab low, which started expelling in the Eocene. So the northwestern Jebel Dhana low right here is probably the one we were most interested in. That was the result of the 2D outputs. So combining this 1D, this understanding from the 1D and 2D, we confirmed that there was a potentially working Diab Upper Thamama petroleum system. The 1D focused on the thermal history and the in-situ maturation at the well locations, and we also calibrated thermal model with the 1D pseudo wells. The 2D gave us regional trends. Of course, there was a lack of a lateral third axis, but at least along the section, we were able to find out how the fluid movements and how the maturation trends were varying along this section. And the 2D results confirmed the observations that we had from 1D. The regional source Diab is actually charging the upper Thamama. Both of these lows may act as sources, but we were interested in the northwestern low because some of the wells in the southeast didn't give us encouraging results or shows. And of course, the maturation results also point to the fact that the northwestern low is actually more mature. There is evidence of some lateral and vertical migration within the block. So this is actually this part right here. And so we are more interested in the Jebel Dhana low. And consequently, we actually drilled a well based on this understanding from the petroleum system modeling. And also we took into account the seismic studies, of course, and the facies modeling and all of those petrophysical results. So the main target was the upper Thamama. And during drilling, we actually observed the early Cretaceous formation to be hydrocarbon bearing more than 10 feet. It was confirmed through MDT sampling, and the interval was in fact perforated, and it actually flowed hydrocarbons to the surface. So this is how we actually managed to confirm our findings and compare the lows and maturation trends in the block. So thank you. I'd like to field any questions you might have.
Hey, thank you for the presentation, Mr. Analava. Do we have any questions from the audience on this presentation? All right, well, that will conclude our session today on field management and exploration. Thank you to all of our presenters, and thank you to our hosts.